Hello scholars, welcome. I'm Mr. Hinkle, and in this lecture we're going to get into the principles of relative dating as developed by Nicholas Steno in the 1600s, and this allowed us to start to understand relationships between different rock layers that led to correlation, which became the foundation of the geological timescale and helped humans understand our Earth in the context of the geosphere. So this is a huge topic, and it's pretty cool. Let's get into it. So 75% of the surface of the Earth is covered with sedimentary rocks. Sediments form from the process of weathering and accumulate in basins. When they accumulate flat, they accumulate long, they accumulate in an order, and these are the principles of relative dating. The Grand Canyon is beautiful, and it's made of sedimentary rocks that are exposed. In fact, the Grand Canyon shows you rocks that go all the way back down to 2 billion years ago. The Vishnu schist at the bottom. That is pretty cool. So relative dating helps us ask questions. Did rock layer A form before rock layer B? Did this organism exist before that organism? So not only does relative dating help us get towards the age of the Earth and Earth processes through time, but it also, sedimentary rocks hold the fossil record, and it allows us to understand evolution, change of life through time, through the context of geologic time. So lots of concepts weaving in and out together here. We've got geologic time, we've got evolution, we've got the relationships of different rocks, the geological time scale, and it goes a little bit like this. The principle of superposition states that. Okay, so if we had a glass, at time 1, I'm going to fill it with this blue liquid. At time 2, I will fill it with the black liquid. Time 3, I will fill it with the red liquid. Now, relatively speaking, time 1 is the oldest, and time 3 is the youngest. And the principle of superposition states, when you have horizontal rock layers in an undeformed sequence, the layers at the bottom are older than the layers at the top. The layers at the top could not form there unless there were layers underneath of them to stack above. So principle number 1, the principle of superposition, the layers at the bottom are older than the layers at the top. Let's keep going. Original horizontality. I love this outcrop. I've been here multiple times. It's in Lancaster. As you're going out towards the Mojave Desert, you could cruise through this outcrop, camp in Red Rock State Park. It's awesome. And what do we see? We see rocks that are all mishmashed and spiraled and smashed together, and they're cut and they're offset. So this is a perfect exposure of faults and folds, which collectively are termed geological deformation. Now, these rocks were not deposited. These are sedimentary rocks. They were not deposited that way. In fact, our next principle, original horizontality, states that when rock layers are deposited, they are deposited originally horizontal, just like it says. Now, there's one caveat to this. In sedimentary basins, at the fringes of the basin, they might be slightly tilted, but they are not faulted and folded like so. So original horizontality And then through plate tectonics, some type of crustal pressures, there's going to be a shift. So now we have our rocks that are forming an anticline, like so. When you look at this, these rocks are folded. You could say they did not deposit that way. They deposited originally horizontal. So, principle number 2, the principle of original horizontality. Let's keep going. The Grand Canyon. Do you like the Grand Canyon? Have you ever been there? The Grand Canyon is awesome. I love it. I've been there a few times. One of my favorite things to do, because I like to run a little bit, is to run from the south rim down to the river and then run up to the north rim, and then you high-five your friend and you turn around and you run back down to the river and then back up the south rim. It's an adventure, run venture, called the rim to rim to rim. You go from one rim down to the river and up to the next rim, and then back down to the river and back to the next rim. I like to run. I also like geology. And when you pair these two things together, it is amazing. But I digress. So if we go back into the Grand Canyon and our third principle, the principle of lateral continuity, it is basically saying that even if there is a canyon as big as the Grand Canyon, if the rocks on either side are the exact same, then at one point they must have continued across that empty space. The only reason they are not there is because of erosion. So here are our sedimentary rock layers that are deposited laterally continuous. And then, over time, you have erosion, like so. So now all these rock layers are gone, and it's just big open space, making a canyon, a Grand Canyon. But now we can infer from the Grand Canyon that this rock layer continued across. The principle of lateral continuity. So we're really stacking them up. Superposition, horizontality, lateral continuity. Next we have cross-cutting relationships. So here's a body of rock, here's a body of rock, here's another body of rock. This is a really cool 3 triple contact rock. So the principle of cross-cutting relationships says that in order for one rock to cut across another, that rock had to have been there first. So let's say here's a sedimentary rock layer. Let's do a couple of them. And then you have geological phenomenon happening. Partial melting is occurring in Earth's subsurface based on some form of magmatic generation, and that is going to cause rock to cut up and across. Maybe this creates a volcano up here, giving us the sedimentary layers and the intrusion. So we'll call this layer A, B, and here is C. Now, if we were to look at the age of these events, or the age of the rocks, what is the oldest rock here between A, B, and C? Let's go old to young. Well, superposition tells us that B is older than A, and cross-cutting relationships tells us that C is younger than both A and B, because it wouldn't be able to cut across these rocks if they weren't there already? Therein lies the principle of cross-cutting relationships. Okay, Steno, he was a smart guy. He really knew what he was talking about. Inclusions is very similar to cross-cutting relationships. So the principle of inclusions goes like this. Look at this big rock. That's a rock hammer. This is so cool. This is a big rock. You've got the pink rock, you've got the black rock, and you've got a chunk of pink rock that's broken off inside of it. So what this principle says is that in order for this rock to be inside of another rock, it must have already been there. So the rock included is older than the host rock. A exists, and then in comes B. And since A exists already, a couple chunks of A break off. Geology's fun. It does weird things. So now, B must be younger than A, because if A did not exist, then these chunks of A could not be inside of B. This is the principle of inclusions. And so when we are trying to figure out the sequence of events, we basically use all of our tools. We say, what's going on here in the world? Oh, look at this. There's a chunk of this and the sequence of events, because this is what we want to do. We want to get to the history of events. Okay, William Stratus Smith. I'll talk about him in detail another day. But basically, he was able to correlate different layers of rock using the fossils that exist within them. He was a canal builder I guess I'll do it now. He was a canal builder in England during the dawn of the Industrial Revolution, was cutting canals to ship coal for industry, and started to notice relationships. Through this, he could correlate over long distances, and he could actually target and identify where the coal was going to be, looking at the fossil relationships that he could see on the surface of the earth. So this is the principle of fossil succession. It's not one of Steno's principles, but it's another one here to help us understand what is older than what and how do we identify different layers. And this is called correlation, identifying different rock layers and how they're similar over long distances. So the Grand Canyon, hey, it's back. The Grand Canyon is such a wonderful example for understanding relative dating. And there's a few key principles in this image that we can see. So you look at the Grand Canyon. Struck by its beauty, I know. So am I. And what principles do you see jump out at you? Well, if we look at this, we've got the principle of cross-cutting relationships where certain layers cut across other layers. We've got superposition as the layers are stacked up. The older layers are at the bottom. The younger layers are at the top. We've got original horizontality. The layers were originally deposited flat. So we can use principles of relative age dating to understand the sequence of events that occurred to create the wonder and the beauty of the Grand Canyon. And it's more than just the Grand Canyon. It's in any basin or anywhere that geologists are trying to understand what the geologic history is. Applying these relative age dating techniques can help to understand that sequence. It also, if we zoom way out, relative age dating started to create the geological timescale, which is kind of like the periodic table of the elements for geology. How did we get there? Well, here is the foundation. So these are the principles of relative dating. We have the principle of superposition, the principle of original horizontality, the principle of lateral continuity, the principle of cross-cutting relationships, the principle of inclusions, and the principle of fossil succession. Thank you so much. We'll see you in the next one.